Okay, so today we're talking about derivatives, and this good news is this is just a review of material that you should have met before. Can everyone remember how to do differentiation? Yes. Can everyone remember what a derivative actually is? The interpretation? Yeah. Okay. Good. So hopefully this should be nice and straightforward today. And the reason we're doing this is because we're going to be moving on to partial derivatives. So last time out, we met functions of more than one variable. So when we have just one variable, it's pretty straightforward what we do in terms of finding a derivative and what the interpretation is. When we've got a function of more than one variable, we have to do something called partial differentiation, which we will cover on Friday. So ahead of that, let's just make sure that you guys have remembered all the stuff about differentiation in one dimension. Okay, so the key thing with differentiation in one dimension is that if you have, say, a curve that is nice and continuous and smooth, which everything you're going to be meeting is in this course, you want to find the tangent at a particular point. That gives you the derivative. Okay, so what's going on? There's a mathematical definition here, and make sure that you're familiar with all the notation, right? Because there are different ways in which we can write derivatives. We can use this little prime notation. We can write df dx and so on. The key thing here is if we imagine we've got a curve, maybe it looks something like this, and we want to find the derivative at a point x. Well, we can just, if we're doing this graphically, we could just draw a tangent at that point and find that that's going to be a straight line in this case, and we can find the slope of that, and that will give us the gradient at that point. Okay. We can also do it algebraically, or there's another interpretation of this where we choose a point a little bit further away. So this point here is at a distance h away from my x. And then we connect these two things up. And then we shrink this h to 0. Okay, so we find the limit of this as h tends towards 0. So what's going on? If we zoom in, we're making this shorter and shorter and shorter until eventually h is infinitesimally small. I've extended it out at this point just to demonstrate what we have, but we have the gradient at that point. Okay, so this is all about rates of change. So if we say have distance and we want to look at the rate of change of distance, we take the derivative of a function, or we look at the slope of the curve. That gives us our speed or our velocity, depending on if it's directional or not. If we take the rate of change of velocity, then we will get acceleration and so on. Okay, so derivatives are all about rates of change. So again, just who watched the pre-lecture material? Okay, good. So we can do it if we've got a function. We can take the derivative of that function and we get some other algebraic expression. We can also, if we have just say a set of points, we can approximate derivatives, and we can do this in one dimension. We'll do very similar things in more than one dimension to approximate partial derivatives. And again, we do a similar thing here by using the formula above. So if I go up here, this was my definition of the derivative in one dimension, where we take a point that's h units apart, and then we let that h tend towards 0. We can approximate the derivative if we have a point. So here we want to approximate the derivative when t is, little t is 8 for our temperature, big T in Seattle. Well, here it actually looks pretty linear, so it's not a great example in some ways, but we take this point here, so that's my t at 8. We take a point nearby. I could have gone here, or I could have gone here to 6, or I go to 10. Here I'm going to go to 10. Make sure you keep the order of these things on the bottom the same. So this is like my h here, the 10 minus 8. That's working out what the change in my x direction is, and change my function values on the top. And this will give me an approximation for what the rate of change is. Okay. So we can use our formula for defining what a derivative is algebraically to approximate derivatives as well. And we'll do this a few times with partial derivatives. This is all kind of boring in terms of remembering your rules for differentiation. It's important to especially remember things like the product, quotient, and chain rule. We will be using these things, but I'm not going to be going through them in detail. I'm going to assume you guys remember how to use them. Okay, so if you can't remember, go back and have a little bit of practice with those things. There should be examples in the textbook as well. And this was kind of a horrible example here, but just demonstrating the quotient rule and also the chain rule. I'm not going to go through that here. Like I said, it's like, what is a derivative? A derivative is telling us something about the rate of change. And with a one-dimensional function, we're going to have the rate of change of a particular point on a curve. If we think about this in a function that has more than one dimension, rather than having a straight line that gives us our tangent, we're going to have a tangent plane. So we're going to be talking over the next few lectures about partial derivatives and how we get tangent planes. And these tangent planes also allow us to do things called linear approximations or linearization at a point. Okay, so we'll come back to those, but that's why we're going through this, is building up to those things there. I don't think there's anything else in particular that needs to be covered. Any questions from pre-lecture material? If not, we can jump straight into some problems. Okay. What I want you guys to do, first of all, is to have a go at calculating the derivatives of these two functions. So a little bit of practice just to make you guys get back into the mindset of taking derivatives, okay? Let's have a go at those and I'll walk around and answer any questions you have. Okay, let's see how you guys got on. Hopefully this should be pretty straightforward. Get the cogs turning again early in the morning. Okay, so for the first one, we've got f of x is x squared minus 3x cubed minus log of x plus 1. So what is f prime of x? Or the f dx, these are the same things. So derivative of x squared is just going to be 2x. Derivative of minus 3x cubed, the 3 comes out the front. So we have minus 9x squared. The log of x plus 1, with minus 1 over x plus 1. Okay. So show of hands, who got that right? Fantastic. Second one, this x square root of x is just x to the half. So we just treat it like a normal power law for our differentiation. Okay, so g prime of x, first derivative, we're going to have the 3 for the exponential just comes up front. So we have 3 e to the 3x minus, as this is just like our power, the power comes out the front. So we have a half x, reduce the power by 1 minus a half. We could write this bit here. Let's rewrite it out again. 3 to the 3x. We could write this as minus 1 over 2 root x if we really wanted to. Okay, these are the same things. Second derivative, we just do exactly the same process again, but with this new function. So we're going to have 9 e to the 3x because this 3 comes out the front again. We have a minus a half, which is going to come out the front here, times by minus half, so we get plus a quarter of x. Reduce this power by 1, minus 3 over 2. You got that one right? Okay, a little bit more mixed that time, but this is, if you're not comfortable with differentiation or you've fallen out of practice with it, go through a few examples, especially ones in the textbook or things you can find online. Tools like Wolfram Alpha are very handy. You can come up with just a function, anything you want that looks like this, and just say, find the derivative of it. So have a little bit of practice. We're going to be using the same rules of differentiation for partial derivatives. So this practice will directly help you with those, okay? Okay, let's move on to something slightly more interesting here. So we have a graph here of the swimming speed of some salmon, and that graph is varying with temperature, so the speed varies with temperature. What is the meaning of this derivative s prime at t? Okay, so for a particular value of t, what is our derivative telling us, and what units is it measured in? Okay, so s prime of t is simply a measure of how S changes as T increases, okay? So S prime of T tells us how S changes as T increases. So in other words, how does the speed at which this salmon swims change as the temperature increases? And its units, well, the units here, we've got centimeters per second on the y-axis. And we've got temperature in degrees C on the x-axis. So this is going to be centimeters per squared per degree C. These are our units. So in a question like this, if you want to work out the units, you take the thing you have here, and you're measuring it in per whatever we have here. Okay, so if this was, say, meters and seconds, if we're doing distance and time, then we would have meters per second, which is why we end up with speed. Okay, if this was speed against time, so if it was meters per second versus time in seconds, then we would have meters per second squared, which is acceleration. Okay, so units, just you can think about it as the thing on the y-axis per the thing on the x-axis. Okay. Now we're asked to estimate the values of our derivative at 2 points when t is 15 and t is 20. So I want you guys to have a go at doing that. Remember that our derivative is defined to be this. Well, I'll tell you what, I'm going to put the approximate in there. So if we define our derivative, we take the limit as h tends towards 0. Now you're not going to take the derivative, you're just going to approximate this. So have a look at this graph here and use this formula to approximate what the derivative is when t is 15 and when t is 25. Okay? Again, I'll go around and answer any questions you guys. Incidentally, whenever we're doing these problems and I'm going around answering questions, sometimes because those questions take a little bit longer, if you finish, feel free to go on to the next problem and get a head start on that, because we won't necessarily get through all of the problems in class, okay? So don't just, if you finish, don't just sit there and play on your phone or whatever, try and go on to the next thing. Okay, estimate these values. So how are we going to do that? Well, the first one we want when t is 15, so t15 is going to be here. How do we estimate this? Well, we need to take a point that's relatively nearby. So I'm going to take t is 20 and draw a line between them. And this is an approximation, right? You might have chosen something that's closer. At the end of the day, it's just an approximation. So our function value, our derivative, when t is 15, is going to be approximately equal to, what do we have? We have our s value when t is 20 minus our s value when t is 15 over the difference in our t values, so 20 minus 15. So what have we got here? So this looks like this should be about 30 centimeters per second. So this is going to be 30. What do we have here? Well, kind of looks like it's maybe around 27. And the difference is 5. So this is approximately 0.6 meters per second, not meters, centimeters per second. Always make sure you get your units right and don't screw up like that. Centimeters per second per degree C. You might have a slightly different answer because this is an approximation. You might have chosen a different point to go from. You might not have chosen 20. You might have guessed that it was a different value at S of 15. That's okay. As long as you're consistent in how you calculated these things, if your answer differs slightly, that's fine. Yeah. I chose 20 because it was closer. So if you can choose something closer, you're probably better, right? So the best thing I could possibly choose would be something that's exactly like right next to it, right? The further I go away, so if I choose 20, you can't choose the exact number because otherwise you'll just end up with 0 divided by 0. And that's essentially kind of what we do in the limit when we let h tend towards 0. But if we're doing this approximation, if, for example, I picked 25, the further I go away, the less good an approximation it's going to be. Okay, so we'll talk in a couple of, I think it's on Monday's lecture, about linear approximations in 2 dimensions. And there, the same principle applies, that the closer you can go, the more your linear approximation will be valid. Okay, so if you choose a further away point, the less valid it's going to be. You can see that this slope here is closer to the actual slope than this one here, because it's closer. Okay, hands up who got something fairly reasonable like that. Okay, great. Let's just run through. We've got time to run through the second one, so I'll do that as well. Okay, so the second one, we are trying to find our derivative when t is 25. So this is t is 25 here. Look at those. So s prime at 25 is going to be approximately equal to, let's say, I'm going to take we can do it the other way around. As long as we're consistent, we're fine. So I'm going to take, again, my S20. This time, as long as the order of the things on the top are the same as the order on the things at the bottom, it doesn't matter. So what I mean by that is I can take my S25 and subtract my S20, as long as I also have 25 minus 20 on the bottom. I could have done it the other way around. I could have said, what happens if I do S20 minus S25 divided by 20 minus 25, okay? Because the signs will cancel each other out. As long as we're consistent, it's okay. So what do we have here? S25 looks like it's about 25, I think. And we previously said that S at 20 was about 30, and then we've got 5 on the bottom. This is going to be minus 5 over 5. So this is going to be minus 1. What are the units? Centimeters per second per degree 6. Okay. This is something that people often miss out. If I was to ask this question in a midterm exam, whatever, make sure you put your units down. If you just left this as minus 1, that's not telling me it's minus 1 what, okay? So always try and include your units. Okay, let's go through this one together because it's a little bit more involved. So here we've got a tumor, and we're told that when the diameter of this spherical tumor is 16 millimeters, it is growing at a rate of 0.4 millimeters per day. We're asked to find out how fast is the volume changing at that time. Okay. So we need to do a few investigative steps here. This diameter, I'm going to call x, measured in millimeters. What do we know about the volume of a sphere? So this is a spherical tumor. We know that our volume is 4/3 pi r cubed. But we're not given the radius. So r is the radius here. We're given the diameter. So we need to do a little bit of manipulation here. So 4/3 pi r cubed is the same as 4/3 pi x over 2 cubed. Why x over 2? Because x was the diameter. So x over 2 is going to be the radius. So if we cube this, we're going to have an x cubed, and we're going to have an 8 in our denominator. So this is eventually going to reduce to a 6th of pi x cubed. So what I've done here is I've rewritten my volume in terms of my diameter, which we're given, rather than the radius. That's the first step here. Now, what do we actually want to work out? We want to work out how fast the volume is changing at a particular time. So the rate of change of the volume is just going to be dV dt. How fast the volume is changing. So what do we know? Well, V up here is in terms of x. It's not in terms of t. But we're given the rate at which the diameter is changing at a particular time. Okay, So we have our dv dx, or we can work out our dv dx by this row above, because v is just a function of x, so we can take its derivative, we can find that. And if we take the product of that and dx dt, which we're given in the question, the dx dt is 0.4 millimeters a day, then, although this isn't quite what happens, you can think of these things as cancelling, and we end up with a dv dt, okay? So we can use our chain rule here to get our answer. So what do we have? We are going to have dv by dx. Let's work out our dv by dx first of all. dv by dx, let's put it over here. dv by dx is going to equal, the 3 comes up front, so we're going to have 3 over 6. That's going to go to a half pi x squared. So we can substitute in a half pi x squared times by our dx dt. So this is still the general formula. So that's why I've left it in this form at the moment. And we want to know how fast the volume is changing when x is 16 millimeters. Okay. So that's why I've not substituted it in yet, because this is the general formula at any value of x, at any value of and any time point. Now we're interested in what's happening when x is 16. So I'm evaluating that derivative when x is 16. So all I need to do now is take a half times by pi, substitute in my x value, and then my dx dt, we were told in the question. So when the diameter of the spherical tumor is 16 millimeters, it's growing at a rate of 0.4 millimeters a day. So the diameter is growing at 0.4 millimeters a day. Diameter is x, so our dx dt at this point in time is 0.4 millimeters per day. This point is just calculation. If you do this, this should work out at 51.2 pi, which is roughly 160.8 what? 160.8, what are my units? Yeah. Millimeters cubed is volume. What have we got here? Per day. Okay. So we've got volume per time. Okay, so volume is in millimeters cubed and time is days. Okay. So this kind of question is one that might sort of stump you at first, right? You think, oh, I'm not given enough information here to work this out. But we can use our chain rule to find an equation for dv dt. So first of all, we can have our v in terms of x. We need our v in a dv dt, so we need some time element, and we're given the time element by knowing this instantaneous rate of change at a particular day. Okay. Have a go at doing this one. Okay, so here we've got a brain size in fish. So we've got brain weight is B as a function of body weight, and we have this model here. So B is in terms of W, where B and W are both measured in grams, and W is the weight of this fish. So we've got B in terms of W. We're told that we also have a model, sorry, I've missed that sentence, a model for body weight as a function of length, measured in centimeters, is here. So we've got B in terms of W, and we've got W in terms of L. And then the other piece of information we're given is that if over 10 million years, the average length of a certain species evolved from 15 to 10 centimeters at a constant rate, how fast was the species brain weight increasing when the average length was 18 centimeters? So there's quite a lot of information here. So actually, I'm going to go through the first part with you and then leave you guys to work out the rest of it, okay? So the first thing I'm going to do is let T be measured in millions of years. So we're told our other units, but we haven't got a measure of time here. I'm going to say it's measured in millions of years. So what do we have? Well, we're told this bit that's underlined, over 10 million years, the average length increases from 15 to 20 centimeters at a constant rate. So because it's a constant rate, we know that our dl dt is going to be a constant. We end up at 20 centimeters. We started at 15 centimeters, so 20 minus 15 on the top. And that occurs over 10 million years. Now, the reason this isn't an approximation like we had above is because we're told that it's a constant rate. If it wasn't a constant rate, if I just had the start and end point, it would have to be an approximation. But if we're told that it's a constant rate, then we know that this is changing gradually over time. Okay, so this works out to be 0.5 centimeter per what? Per million years. This is the rate of change of length. And what do we want to do? We want to find how fast the brain weight is changing. So dB, dt. So because we're talking about how fast it's changing, it's dB in terms of time when the length is 18 centimeters. Okay, so this is what we want to find. We've got dl dt. We've got b as a function of w and w as a function of l. So you want to write, first of all, what is dB dt using the information you have above. Okay, the clues you'll need to use the chain rule. So have a go at that for the next few minutes. Okay, the last thing is just thinking about something visually in terms of what it means when we have a function and we look at its tangent. This question here, again, it's not the kind of question I'm going to be asking you guys on a midterm or a final. It's just to help you visualize what's going on with the curvature of a function and a tangent to that curve. Okay, so we're trying to work out, given a graph of a function, can we find, or given a function, can we graph it and work out whether our tangent is above or below that line? Okay, so if we were to actually graph this out, we would have something that looks like this. This is my x, and this is my f of x, which is 1 over 1 plus x squared. So when x is 0, we know that we're going to be crossing 1. Incidentally, being able to go from having a function and sketching that out is something you guys should be able to do. So that's something I expect you to be able to do, okay? If you're given a function that's not too complicated, you should be able to take it forward and sketch it out. Okay, so it crosses when x is 0, f of x is going to be equal to 1. As x gets really, really large, the denominator is going to get really, really small. So as x tends towards infinity, f of x is going to tend towards 0. So I know that this graph is going to look something like this. And we're asked to work out whether my tangent is above or below the axis when x is equal to 1. Okay, so when x is equal to 1, we can have f of x is 1 over 1 plus 1 squared, so a half. So this is the point I care about here. X is 1, f of x is going to be a half. Now we can already tell that this gradient here, if I was to draw my tangent line and extend it out, that it is going to be below this axis. But we can also work this out algebraically. So suppose you didn't want to sketch it out on like I've done now, or it was a more complicated function, how would we do this? Well, we need to look at our second derivative. Okay, so let's work out what our first derivative is. Our first derivative, again, I'll go through this a little bit quickly because this is just quotient rule, power rule, and chain rule, so things that you should already know. Take my word, hopefully if I haven't made another mistake, this is minus 2x over 1 plus x squared all squared for our first derivative. So that's telling me the slope of my tangent at a particular value of x. But I want to know, is this tangent above or below the axis? So I want to know whether my function is concave down, in which case it looks like this, and my tangent will be above, or if it's concave up, which looks like this, which we can tell from the graph it's going to be concave up, but we want to show that that's the case, in which case my tangent is below. Okay, so you can think of this as if it was a surface. We'll talk about surfaces and tangents tangent planes. If my curve is coming like this, then my tangent is below. Whereas if, oh, that was dangerous. Whereas if it's going up like this and it's concave down, then my tangent will be above the plane, okay? So take my second derivative here. If you take the second derivative, again, trust me, it works out to be 6x squared minus 2 over 1 plus x squared cubed. Okay. So now what do we want to do? Well, we want to look at the point x is equal to 1. And if we sub this into my second derivative, we get 6 times by 1, which is 6, minus 2 over 1 plus 1 squared, which is just going to be 2, all cubed. So over 2 cubed, which is 4 over 8, which is a half. The key here, if you look at your second derivative, this is positive, and because the second derivative at this point is positive, that means our function is concave up. So when the second derivative is positive, that means our tangent is below the curve. If this was negative, it would mean our tangent was above the curve, okay? So this kind of question, we could either sketch everything out and find out what's going on, or we can look at our second derivatives, okay? So part of the reason I wanted to mention this is that later in the course, we'll be talking a bit about second derivatives and how we can use those second derivative tests to work out whether we've got maxima and minima, okay? All right, thanks very much, guys. I'll create those solutions and post them online, okay?